In the previous video, we introduced dynamics, a branch in mechanical physics that studies the forces that cause changes in motion. We explored the first two laws of motion by Sir Isaac Newton, and we took a close look at two fundamental concepts, velocity and acceleration. Now that we've covered the essential theory, it's time to dive into the implementation. As always with my tutorials, I'm making very basic use of C++, so if you are familiar with this programming language, you should have no problem following along. I'm using Visual Studio Community Edition on Windows as my development environment. In addition, in each tutorial directory, you can find build scripts for Linux. I've set up a new folder in my Visual Studio solution called Physics for Game Dev. The core of this setup is the physics system project, which will house the fundamental data structures and algorithms required to simulate physics in our games. The output of this project is a static library named physicsystem.lib, which will be generated in the ogldev/windows/lib directory. Every tutorial in this series will link against this library. At the moment, the physics system project includes a few header and source files, but this will naturally expand as the series progresses and we introduce more features. Alongside this, there's a tutorials folder. Nearly every video in this series will be accompanied by a dedicated project here. Each tutorial will typically rely on a single source file, located under its own folder in ogldev/physics-for-gamedev. For visualization in this series, I'll be using the framework developed in my OpenGL tutorials. However, I'll make as few assumptions as possible about the graphics API so that you can easily adapt the same principles to your own rendering setup. At a minimum, you'll need the ability to render a basic 3D object, a dynamic camera that can move and rotate, a main render loop that runs while the window is open, and a mechanism to calculate the delta time between frames. I'll assume you have a function that handles per frame updates. This usually includes managing the camera, dynamic state, and any necessary OpenGL or other API calls. At the end of each frame, we'll use glfw to swap the buffers and poll for events. This is all standard OpenGL workflow. Nothing fancy, just the essentials to get a physics simulation up and running with visual feedback. The tutorial file includes an application class, which usually derives from base GL app. This is how I connect to my OpenGL framework. This class includes a function called onFrameChild, which is the entry point from the main render loop. In addition, the class includes an attribute of the system class defined within the physics namespace. This system object is provided by the physics system project, and it serves as the core interface to all of our physics calculations. Inside onFrameChild, we call the update function on the physics system object, passing in the delta time in milliseconds. This allows the physics simulation to advance in sync with the rendering loop. To access the physics system, we need to include the header file physicsystem.h. Now let's take a closer look at the physics system class itself and explore how it manages the simulation state and integrates with the rendering pipeline. All the code in this project resides within the physics namespace, making it easy to identify and manage interface points between the rendering system and the physics engine. The main class here is called System. It contains a few private attributes. A vector of PointMass elements, this is basically the particle. We also have an update listener, which is a pointer to a function, and the number of active particles in the vector. One of the major design decisions when implementing a physics framework is the question of the interface between the two systems, rendering and physics. On one hand, we want the two systems to be as independent as possible. This will allow us to integrate each system into different projects with minimal changes. We also want to be able to take advantage of multi-core CPUs and execute each system on different threads. On the other hand, we want the interface to be simple and efficient. From a purely performance perspective, the best thing is to allow the physics system to directly manipulate the position attribute of a 3D object. The rendering system can then render the object in the new position. But in my opinion, this is too intrusive. Therefore, I created the concept of an update listener, which is a pointer to a function that takes a void pointer and the reference to a vec3 as parameters. When we initialize the system class, we provide the number of point masses that it needs to support and an address of an update listener function. PointMass is a synonym for a particle. The update listener is optional and can be null for testing, debugging, and etc. Its main purpose is to let the physics system notify the client, or the rendering system in this case, about a change in the position of a particle. The flow is as follows. After initializing the physics system, the client calls alloc PointMass. The result is a pointer to a PointMass object. This class includes a few physics-related attributes, such as the center of mass, or the position, the linear velocity, the sum of forces acting on the particle, and the mass of the object. In addition, there is a void pointer called target, which represents the sibling of this object in the client system. In our case, this is the scene object in the rendering system. The scene object contains attributes such as position, rotation, and scale, and points to a model object, which is what the system actually renders. Other names for the scene object which you may be familiar with are actor or entity. The PointMass class provides a convenience method for initialization. In the sample code, we initialize the physics system with some particles and an update listener. We allocate a couple of point masses and initialize them with some mass, the position of the scene object, a force vector, and a pointer to the scene object. This address is set into the target pointer in the PointMass object and used when calling the update listener. So let's take a look at this function. We can safely cast the p-object pointer back to the scene object class because we know what this pointer actually points to, and we can call setPosition on the scene object using the position from the physics system. The corresponding object will be rendered in the new position. Of course, in the future, we will extend the listener with more stuff, such as a rotation vector or quaternion or whatever. But for now, this interface is enough. This keeps the two systems nicely separated. The client knows the interface of the physics system, but the physics system doesn't need to know anything about the client. Obviously, there are many options for setting up this interface, so let me know your thoughts in the comments below. Now let's see how the physics system actually works. The initialization is very simple. We save the pointer to the update listener and resize the vector according to the number of point masses requested. As we've seen in the onFrame child function, the physics system update function is called on every frame, with the delta time as a parameter. In my implementation, the delta time happens to be in milliseconds, so first of all we have to convert this to seconds by dividing it by 1000. This is because the common unit of time in physics is seconds. Next, we traverse the number of active point masses and call the update function on each element with the delta time and update listener as parameters. This function starts by calculating the linear acceleration. The second law of motion tells us that the force is a product of the acceleration and mass, so the acceleration is the force divided by the mass. We can now increment the linear velocity by the product of the acceleration and the delta time, and then the center of mass is translated by the product of the linear velocity and the delta time. Finally, if an update listener was provided, we notify the client using the target pointer and the updated center of mass. The target pointer probably points to a scene object in this case, but the physics system doesn't need to know anything about it. So the physics system updates the position of all the particles it manages, and the rendering system renders the objects in their new position. We can initialize the point masses and see how different masses and different forces result in differences in acceleration and velocity. Another simple experiment that we can implement is to place the object somewhere high up and apply gravity on it. Unfortunately, we still don't have proper collision detection with the ground, so the object falls right through. For the sake of this video, I've added a simple check in the update listener as a workaround. So that's it for today. Thank you for watching, and I will see you next time.